Our world runs on power. We have an insatiable, ever-growing appetite for electricity that keeps our cities bright, our industries moving, and our digital lives online. But for the last century, we've been hooked on fossil fuels, and it's pushing our planet to a breaking point. The climate is changing, and the world we've taken for granted is starting to wobble. To try and fix this, humanity is making two massive, almost mythical, bets on the future of energy. One bet is on perfecting a 70-year-old technology that comes with a dark and complicated past. The other, it's a bet on building a literal star right here on Earth. The outcome of this quiet clash, between the practical and the profound, the upgrade and the dream, is going to define our world for the next 100 years. This is the story of the two nuclear futures battling to power the world. The old guard, reinvented advanced fission. The first bet is on nuclear fission. If you picture a big, unstable atom, fission is basically splitting it apart. When it splits, it unleashes a crazy amount of energy. We've been using this process for decades to generate huge amounts of very low-carbon electricity. But let's be honest, this tech has baggage. The names are infamous: Chernobyl, Fukushima. The images are just as stark: giant cooling towers and those yellow barrels of radioactive waste. For a long time, the public has seen nuclear power as a necessary evil at best, and a catastrophic risk at worst. The big three fears, meltdowns, waste, and cost, pretty much stalled the industry in its tracks. But what if that story is finally starting to change? This isn't about your grandfather's nuclear reactor. This is about advanced fission. It's a quiet revolution happening in nuclear engineering, one that's tackling those old problems head-on. The goal isn't just to build another power plant, it's to build one that's fundamentally safer, makes less waste, and can be built way faster and cheaper. A huge part of this is the idea of passive safety. Older reactors needed a ton of complex, active systems, pumps, backup generators, and people ready to flip switches, to prevent a meltdown. If any of that failed, you could have a disaster. Advanced reactors are designed with a totally different philosophy. Safety is built right into the physics of the machine. Many new designs use coolants like molten salt or inert gas instead of high-pressure water. In some concepts, if the plant totally loses power, a specially designed frozen plug just melts. The fuel then automatically drains into a secure tank, and the reaction just stops. No buttons, no computers, no frantic human intervention needed. It's designed to fail safely. Then there's the fuel itself. One of the coolest innovations is something called TRISO fuel. Picture a tiny grain of uranium smaller than a poppy seed, then wrap it in multiple layers of super strong ceramic and graphite. The US Department of Energy once called it the most robust nuclear fuel in the world. That microscopic armor is designed to be incredibly resilient, containing radioactive material even at extreme temperatures and dramatically reducing the risk of a dangerous release. Companies like X-Energy are designing entire reactors around this idea. And this isn't just on paper. In Wyoming, TerraPower, a company co-founded by Bill Gates, is preparing a site for its Natrium reactor, right next to a retiring coal plant. After some earlier delays, site prep is done, and they're moving through the final regulatory steps to start construction. It's a new type of reactor cooled by sodium, and it's designed to store heat in molten salt, so it can ramp up power whenever the wind stops blowing or the sun goes down. It's not just a US thing, either. In Canada, site work and licensing are moving along for an SMR, or Small Modular Reactor, at the Darlington site, with a goal to have it online around the end of the decade. SMRs are a huge part of the plan. Instead of massive, one-off projects that take forever and cost billions, SMRs are designed to be smaller and built in a factory, making them faster and cheaper to roll out. This is the promise of advanced fission, a reliable, 24/7 clean energy source that actually learned from the mistakes of the past. It's not science fiction. In fact, tech giants are already exploring partnerships to one day power their massive, energy-guzzling data centers with these next-gen plants. But what if we could get rid of the core risks of fission entirely? What if, instead of splitting atoms, we could smash them together, releasing even more energy with none of the historical baggage? The audacious newcomer fusion. This brings us to humanity's second big bet, nuclear fusion. This is what powers the sun. Instead of splitting heavy atoms apart, fusion forces light ones together, usually types of hydrogen, like deuterium and tritium. When they fuse, they create helium and a neutron, and release a mind-boggling amount of energy. Fusion has been called the holy grail of clean energy for a few big reasons. First, the fuel is just about limitless. Deuterium can be pulled from regular seawater, and tritium can be produced by the reactor itself. Second, the risk profile is completely different. The reaction is incredibly hard to start and even easier to stop. If anything goes wrong, the plasma just cools down and the reaction fizzles out in seconds. A runaway, Chernobyl-style meltdown is physically impossible. Third, while it's not perfectly clean, it's a huge improvement on waste. Its main byproduct is harmless helium, and while the process does create radioactive material by activating the reactor walls, this waste is much less nasty and has a shorter half-life than traditional nuclear waste. We're talking decades or centuries, not thousands of years. So, if fusion is so great, why don't we have it? Well, because building a star on Earth turns out to be one of the hardest things humans have ever tried to do. To get fusion going, you need to heat fuel to over 100 million degrees Celsius, way hotter than the core of the sun. Then, you have to trap that superheated gas, called a plasma, so it doesn't touch and melt the walls of the reactor, and hold it all together long enough for fusion to happen. For decades, the running joke was that fusion power was 30 years away, and always will be. And for a while, that was true. The main effort was a massive, international government experiment in France called ITER. It's designed to prove fusion can create more energy than you put in, which is a vital scientific step. But it's not a power plant, and its timeline has stretched, with full power operations not expected until the late 2030s. But over the last few years, the game has completely changed. A whole new wave of private companies, backed by billions in venture capital, is racing to build a commercial fusion plant on a much faster schedule. Companies like Commonwealth Fusion Systems, which spun out of MIT, are using powerful new magnets to build a smaller, stronger machine they believe can generate net energy and lead to a commercial power plant in the early 2030s. Another big name, Helion, made waves by signing an agreement to supply Microsoft with fusion-generated electricity, targeting a start date as early as 2028. They've reported reaching incredibly high temperatures in their prototypes and have been preparing to build their first commercial-scale machine in Washington. While that 2028 timeline is seen by almost everyone in the field as incredibly ambitious, the fact that a company like Microsoft signed on shows a massive shift from pure theory toward commercial reality. The dream is getting closer. The old joke is starting to fade. But there are still huge hurdles. Can these companies turn a physics experiment into a durable power plant that can run for years on end? Can they figure out how to produce enough of their own tritium fuel? And can they do it all at a price that actually competes? These are the billion-dollar questions they're trying to answer right now. The head-to-head. So how do these two nuclear futures actually compare? It's a fight between timelines, technology, and risk. On one side, you have advanced fission. Its biggest advantage is that it's ready to go. The tech is here now. Companies are already preparing to build commercial plants. Its main challenge is its own history. It still produces some long-lived nuclear waste, which is technically manageable but politically toxic, and it has to overcome decades of public fear about safety, even though the new designs are a world apart from the old ones. On the other side is fusion. Its readiness is its biggest weakness. It's still mostly experimental, and widespread commercial power is likely still a couple of decades away, at best. But the payoff is enormous. Its fuel is nearly infinite. Its waste is far less problematic. And its safety profile is a game changer. A catastrophic meltdown just isn't in the cards. Fission is the seasoned veteran that's been through a modern makeover. It offers a clear path to getting huge amounts of carbon-free power on the grid within the next decade. Fusion is the audacious rookie, the moonshot that could solve humanity's energy problems forever. So, which one wins the battle for our energy future? The truth is, this probably isn't a battle with a single winner. It's more likely a story of partnership, of one technology building a bridge for the other. Advanced fission is the bridge. It's a technology we can start deploying in the 2030s to fight climate change and meet our soaring energy needs. It can provide the reliable, 24/7 power we need to retire fossil fuels for good, backing up a grid that will be dominated by solar and wind. It's the practical, near-term solution that buys us precious time. Fusion is the destination. If, and it's still a big if, it becomes commercially real, it will be a turning point for human civilization. A future of clean, safe, and abundant energy. It's the long-term dream that could power our world for thousands of years. The quiet battle between these two futures isn't really fission versus fusion. It's a story about how we navigate the next few, critical decades. It's about ambition meeting the laws of physics, and engineering trying to build a cleaner world, without pretending the hard parts aren't there. That future is no longer just a drawing on a whiteboard. It's being built, right now. If you enjoyed this look into the tech that's shaping our future, make sure to subscribe and ring that notification bell. Which horse are you backing in the nuclear race? Let us know your thoughts in the comments. Thanks for watching.